Welcome to the presentation of my doctoral thesis. My name is Moritz Merk, and the next 20 minutes I will talk about comprehensive and consistent linear models which help to gain understanding and also for predicting thermoacoustic phenomena in gas turbine combustors. Now, before we dig into the details, let's start with some motivation. We all know the global temperatures are rising due to the emission of greenhouse gases within the last century. However, still today, about 70 to 80% of worldwide energy used is still generated by combusting fossil fuels. And to avoid these emissions, the electrification of end users combined with the simultaneous switch to renewable energy sources is key. However, we all know that renewable energy sources such as wind and solar power are subject to natural intermittencies, which we must counterbalance to ensure a reliable energy supply and a stable power grid. Now, gas turbine combustors with their high operational flexibility can do exactly that, either by still burning hydrocarbon fuels such as natural gas in transition to a fully renewable power grid, as long as there are still not enough large-scale storage capabilities for renewable energy available. Or even beyond that, if we would store renewable energy in chemical form, such as hydrogen. Now, there's a problem with gas turbine combustors. For low NOx emissions, they are typically operated close to the lean blow-off limit. However, in that regime, they become susceptible to thermoacoustic instabilities with undesired consequences ranging from reduced efficiencies over predominant wear or even to the destruction of the combustor. Now here we have a very famous example. On the left-hand side, a new burner assembly, and on the right-hand side, the same burner assembly after operation featuring thermoacoustic instabilities where it's completely destroyed. So it's quite clear that we must avoid these instabilities during operation. Now, for short, what are thermoacoustic instabilities exactly? Well, it's a resonance phenomena resulting from the feedback loop between acoustic perturbations and a modulated heat release, in our case, a flame. For example, if we have an acoustic perturbation entering the combustion chamber here, modulating the heat release of the flame, then this modulated heat release will act as a source of sound itself. The additionally emitted acoustic perturbations may propagate downstream, get reflected at the end of the combustion chamber, propagate upstream again, and once again modulate the heat release, and thus closing the thermoacoustic feedback loop. Now, in addition to acoustic perturbations, vortical, entropic and compositional perturbations may also contribute to thermoacoustic feedback loops when, for example, they are generated within the flame region, convected downstream, and then accelerated within the first turbine inlet guide vanes. So, this acceleration of these perturbations will generate additional acoustic waves, which then may propagate upstream again, modulating the heat release and thus closing the feedback loop. So it becomes quite obvious that overall there is a large variation of different theoretical feedback loops possible, which may incorporate different physical effects. And yeah, this complexity combined with the undesired consequences is the reason why we would like to have prediction models to help with the development of gas turbine combustors. Now, the development of, or the modeling of thermoacoustic phenomena, both for gaining understanding and also for predicting, was the topic of this thesis, and 4 contributions were made at different stages of the modeling process. And now we will shortly review what questions these contributions were asking and at which stages in the modeling process the contributions were made. Now, before we can start to build a thermoacoustic model, we must understand the underlying physical mechanisms which are essential for our thermoacoustic feedback loop. And this was basically the focus in our first contribution, where we asked the question how to consistently analyze thermoacoustic sources in general three-dimensional flows. And we will talk a little bit in more detail about that in the first part of this presentation. Now, after we understood what the essential underlying mechanisms are, we can start to build a thermoacoustic model incorporating these effects. Now, in a linearized or linear modeling world, these may range from fully three-dimensionalized or three-dimensional discretized models down to, for example, network models. Now, network models approximate the system by the interconnection of simplified subsystems. For example, here for a simple slit flame, we approximate it by a duct element, followed by an acoustic or an area change, followed by a flame, followed by a duct. Now, within thermoacoustic network models, there are special elements which in addition assume that the wavelength of acoustic and convective perturbations are much larger than the spatial extent of the system itself. And if this is the case, we can approximate the subsystem by a sudden jump in state variables, and we call this approximation a jump condition. And our second contribution was basically focusing on the derivation of such jump conditions and asked the question, can we avoid the repeated derivation of jump conditions representing the same subsystems in different application cases, as it's usually the case currently? Now, this will be the second part of today's presentation. Moving on, within thermoacoustic models, the flame is typically a little bit of a tricky thing because the flame dynamics are typically so complex that we cannot really model them analytically for complex setups. So most thermoacoustic models rely on getting the flame dynamics as an external input, which is previously computed either by high fidelity simulations or determined experimentally. Now, our third contribution was focusing on the experimental part, and it asked the question how to consistently infer the flame dynamics from experimental pressure measurements in test rigs with complex features such as, for example, a bypass annulus, effusion cooling, or downstream end contraction, because the state-of-the-art approach is no longer working in this case. Great. Last but not least, after we're done with the whole modeling process, we typically want to assess the stability of our system, and one way to do it is basically by solving the thermoacoustic eigenvalue problem. The result of this problem will be the information of the eigenfrequencies and the information if the specific eigenfrequency is stable, so decreasing has a decreasing amplitude with time, or if amplitudes increase over time and the eigenfrequency is unstable. Now, in our fourth contribution, we basically asked the question how to solve the thermoacoustic eigenvalue problem reliably, efficiently, and accurately. And we basically did a comparison between two methodologies, the contour integration method of Bain and solving an approximate linear eigenvalue problem. Great. Now, after we know what contributions were made within this thesis, it's time to dig a little bit deeper. However, due to time constraints, we will only talk about the first two contributions. For the second two contributions, I refer you to my thesis. So let's start by talking about the consistent analysis of thermoacoustic sources. Now, by analyzing thermoacoustic sources, we can get an insight into the underlying physical mechanisms and their importance in various physical configurations. However, for that, we must identify the analytical source terms. Fortunately for us, we know that these source terms are intrinsic to the linearized differential balance equations of mass, momentum, energy, and species. So the task is basically simply isolating these source terms from all the other terms, which will be the propagation terms, by reformulation, that system of equation. However, the strict isolation of source terms is not as straightforward as one might think and comes with its own pitfalls. And we will talk about that now. So let's assume I want to analyze the source terms of convected entropy perturbations. For that system, what people typically do is to say, well, the propagation operator or the convective operator, I know how that looks like for this case, and it looks like this. Now then people reformulate the system of equation and get all the other terms on the right-hand side and call them the source terms. Now there's a problem with that thinking, and we will show that for the simple example of a 1D propagation stabilized perfectly premixed flame at low Mach numbers, which is plotted here in an entropy over a space diagram where this entropy gradient basically represents the flame. Now, if such a flame becomes subject to velocity perturbations, the reaction rate of the chemistry does not change because, well, it's simply not sensitive to it. So what the flame will do in response is basically it starts moving simply to adapt or to keep the reacting mass flux through the flame front constant. Now, since this flame does nothing but adapting its position to keep the kinematic balance constant, there are no sources of entropy perturbation within this test case. So what we would like to see from a strict isolation of source terms is that they are zero within the whole full domain. And this would translate in the requirement that we would like to see at each observation point a constant entropy signal over time. Now, the problem with the convective operator formulated up here is that it's formulated in an Eulerian reference frame, which basically means that we observe our system at fixed spatial points, for example, x star. And if we now plot the entropy signal at this position over time, we clearly see it's not a constant line, but there's clearly some disturbance of entropy. And this means, on the one hand side, that what we see here is not a strict isolation of source terms. Something is still not fully correct. And now the question arises, where does it come from? Now, if we look at this left graph, it's rather clear. This perturbation we see is merely an artifact due to the movement of the flame relative to our observation point. And by understanding this, the solution to get rid of this artifact is rather simple. Well, let's just take a reference frame which tracks our source region, which is, for example, an arbitrary Lagrangian-Eulerian reference frame. If we do that, we see on the right-hand side the entropy signal we want to see, a constant line over time. And mathematically, that means that we do no longer take the temporal derivative at a fixed spatial point, but at a fixed coordinate of the moving arbitrary Lagrangian-Eulerian reference frame. And on the other side, we get an additional source term, which is basically a correction term which corrects the mass flux through the flame front due to its own movement. Now, within our CNF paper, we did this extensively, derived the full equation for the generation of entropy perturbations. We simplified it to a quasi one-dimensional jump condition, analyzed all the non-diffusive cases, source terms, and explained it with temperature entropy diagrams. In addition, we did an order of magnitude analysis and basically showed that for lean premixed flames, the heat release per unit mass is the dominant source mechanism, which basically means dominant entropy perturbations in lean premixed flames are merely generated by equivalence ratio perturbations. Now, for the details, I refer you to our combustion flame paper. And yeah, now let's move on and talk about the derivation of jump conditions. Now, within the next slides, we will exemplarily talk about the derivation of a compact flame, such an element which is shown here, which is basically a representation of the simplified system as it's shown here, where we have a flame front which is in a constant cross-section duct. The flame front might adapt its position due to incoming perturbations, and the inlet and outlet fluxes are assumed quasi one-dimensional. Now, the problem with the common way of deriving such a jump condition is that this derivation is typically done with a specific application case in mind. For example, let's say I want to approximate the transfer behavior of a propagation stabilized flame in a single stage combustor. Now, there typically mean flow Mach numbers, incoming mean flow Mach numbers are not that high, such that I could say, okay, I only want to retain terms up to first order in Mach number and neglect all higher Mach number terms. What I would do then is typically, well, I would introduce this assumption in the system of balance equations, derive from this simplified set a jump condition, and finally apply the jump condition to my application case. And this works perfectly fine for this application case. However, if someone else comes along with a little bit of a different application case, for example, let's say a second stage reheat autoignition flame. There typically Mach numbers are a little bit higher, so I could say, well, I would like to also include Mach number terms of second order or even higher order. Then, since our original jump condition here was derived based on a simplified set of balance equations, I cannot use it anymore, and I basically need to start from scratch and rederive a new jump condition. And that this happens repeatedly, simple or a short example down here, a list of 6 papers. It's definitely not extensive, but it clearly shows, jump conditions which basically represent the same element, a compact flame, but distinguish themselves by the approximation order in Mach number they use. If they use realistic or constant gas properties, if they take into account acoustic perturbations, entropic perturbations, compositional perturbations, and if they account for the movement of the flame. Now, to avoid these repeated derivations of these jump conditions, we proposed a Jacobian-based framework which enables us to derive comprehensive jump conditions, incorporating acoustic, entropic, and compositional perturbations with minimal initial assumptions. And after we derived such a comprehensive jump condition, we have the advantage that basically for each application case, we can introduce the assumptions we want to introduce, for example, to achieve a higher efficiency, and then apply it to our application case. And like I already said, we can do this for each application without rederiving the jump condition. Now, once again, I spare you the mathematics within this presentation, and I refer you to our CNF paper. However, we derived in our CNF paper the jump condition exemplarily for a one-dimensional H2 reheat autoignition flame at Mach numbers 0.1 and validated it against a full spatially discretized model. And well, we see here some scattering coefficients in the first line, some absolute value of the scattering matrix in the second row, the phase values, everything over frequency. And we see that for all coefficients, the comprehensive jump conditions, which is represented by the red line, matches the validation data, the black squares, excellently. And the other scattering matrix coefficients look similarly good. However, we left them out for due to space reasons. It's a rather large scattering matrix here. So if you want to have a look at it and you're interested, just search for our CNF paper. All right, so let's wrap up and conclude. So what did we do? We showed that for a consistent source term analysis, we must track the source region, for example, with an arbitrary Lagrangian-Eulerian reference frame. And we did that in our CNF paper exemplarily for the generation of entropy perturbations. Next, we proposed to derive comprehensive jump conditions with a Jacobian-based framework to avoid repeated derivation of jump conditions for different application cases. And in addition, the modularity of this framework makes the framework easily applicable, implementable, and a posteriori adjustable. Third contribution, even though we didn't talk about it in detail, how to infer the flame dynamics from realistic test rigs with complex features. Well, we basically showed that we require a model to bridge the gap between our measurement point and the flame. And we developed a mathematical framework to do so. And last but not least, how to solve the nonlinear thermoacoustic eigenvalue problem. Well, while both the contour integration method and solving an approximate linear eigenvalue problem are capable of computing all relevant thermoacoustic eigenmodes, the contour integration suffers a little bit from hard to set user input parameters, while we can avoid that by solving an approximate linear eigenvalue problem, which in addition usually comes with a speedup. So that's it from my side. Thanks for listening and goodbye.